Electric flux. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Electric flux is a scalar quantity and is denoted by phi. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time v ds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is, to v bar, but makes an angle theta with it, the projected area in a plane perpendicular to v is v ds cos theta. Therefore, the flux going out of the surface ds is v bar dot n cap ds. For the case of the electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. This means that if we place a small planar element of area delta S normal to E bar at a point, the number of field lines crossing it is proportional to E delta S. Now suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta. When theta equals to 90 degrees, field lines will be parallel to delta S and will not cross it at all. Thus, the area element vector delta S bar at a point on a closed surface equals delta S n cap, where delta S is the magnitude of the area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. The electric flux delta phi through an area element delta S bar is defined by delta phi equals to E bar dot delta S bar equals to E delta S cos theta, equation 1, which, as seen before, is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E bar and delta S bar. For a closed surface, with the convention stated already, theta is the angle between E bar and the outward normal to the area element. Notice, we could look at the expression E delta S cos theta in two ways. E delta S cos theta, that is, E times the projection of area normal to E bar, or E perpendicular to delta S, that is, component of E bar along the normal to the area element times the magnitude of the area element. The unit of electric flux is Newton meter square per coulomb. The basic definition of electric flux given by equation 1 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements. Calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is phi approximately sigma E bar dot delta S bar equals to sigma E bar dot delta S bar, equation 2. The approximation sign is put because the electric field E bar is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 2 is written as an integral.